So in topic 9, we are talking about water treatment, and we started off kind of just getting into it as to why we want to treat water. And we were talking about mostly at this point coagulation and sedimentation, which the sedimentation is also called clarification. So we're talking about a lot of the things that are in water, things like clay, which is very relevant to the Athabasca River where we get our water, and how we put alum in there that allows things to clump and sediment, and that's about what we had talked about. We're going to come back and talk about this a little bit with something called flocculation. I'll get there in a minute. But the next thing to talk about is filtration. So most of us are familiar with filtration in some form or another, especially if we've been in the chemistry lab. You know that filtration involves putting your sample through a filter. In the chemistry lab, we're using paper filters of some sort usually. But a filter is basically a porous material that allows the liquid to go through and traps stuff, right? Insoluble stuff or whatnot. Now, we can't do this for drinking water. It'd be a lot of paper. It'd actually be way too slow. You know how this goes dripwise. So for large volumes of water, what we use is sand filtration. So sand filtration is literally just that, where you're using sand and the water goes through the sand and large particles can get trapped on the sand. And that's basically all you're doing. And I'll show you the design of how this works. We're going to get a chance to make a primitive sand filter in lab 7. You're going to get a chance to try to make something like that, but usually the way these works, and there's lots of different designs, but they have sometimes they're layered or they have mixed of various things in there. You can see in this particular sand filter there's different sizes of filter media. So you have the gravel down here, so this would be larger media, and then sand up there. And the way this works is that water is going to come in probably through the top, and it's going to go down and through the bottom somehow. I'll show you, there's a little bit of a better picture here. I'll show you of a sand filter design. And you can see over here, the water is going in. And so it kind of goes in through the top, and they don't want to disturb the sand. So the water doesn't hit the sand directly. It kind of goes in through the side here and then comes around and then goes through the filter media. And you can see the same idea here is they have sand and then they have gravel, and the water looks like it's exits somewhere down here at the bottom. And it's going to trap a lot of large particles. Any flock that's left over, those kind of things, is all going to be good. You can notice there's another drain here, over here on the other end. This is for backwashing. So maybe I'll write that down. This is for backwashing. So the way the backwashing works is that this eventually will get clogged up and they need to clean it. So they push water through the whole thing backwards and try to basically clean the whole thing out. And that's what it's for. So like I said, there's tons and tons of designs of these things. And sometimes they talk about fast sand and slow sand, and I honestly don't really know what the differences are. It just has to do with the sand and the flow right through and those kind of things. But generally for the backwashing, they're doing that every 1 to 2 days, so 24, 48, 72 hours, kind of just depending on the volume of water that goes through and how dirty it is, basically. So here's one of the sand filters at the local water treatment plant, and it has anthracite in it. I'll talk about that here in a minute, what that is. It's basically charcoal, but I'm not exactly sure of the design, but the water goes in and then it's kind of slow, but if you stand there for about 10 minutes, you can see the water level basically slowly going down. So I think the water comes in through the top somehow, and then it sinks through the filters eventually. They use quartz sand. I don't know what the advantage or disadvantage of quartz sand is, or even what quartz sand is entirely. Obviously, it probably has quartz in it. The one day that we were there for a tour, we were fortunate enough that they were going to backwash the whole thing. And here's the system backwashing. So like I said, this is basically water coming through the whole system backwards and allowing them to clean out the sand filters. There's many types of filters out there, by the way. If you take a look here, this is showing some more, I guess you would call higher quality filters that we have in the lab. These are tiny little, this is about 1 inch in diameter, these discs, and it's made of something other than paper, usually some sort of polymer. And you can see that there's pore sizes there. So these filters here are often used when we have a solution and we're trying to sterilize it. And so you can get a filter, and usually what you do is you get a filter that's 0.22 micrometers. That means the pores are 0.22 micrometers. And what that is going to do is basically filter out all bacteria. Anything smaller than a bacteria will fit through, but it's going to make it mostly or pretty close to being sterile in a very simple process. These are for larger volumes, and there's all, like I said, all sorts of different types out there. So back to the anthracite. You can see I don't have the name on here. Anthracite. Anthracite. What is anthracite? Anthracite is basically charcoal. So what is charcoal? Charcoal is wood that is, or it's usually wood anyway, that's partially burnt. So it goes by a whole bunch of names. Sometimes it's called anthracite. Sometimes I just call it charcoal. And sometimes you hear people calling it activated carbon. And so what's the big deal about charcoal? So what you have is this wood that is partly combusted, and it basically, it has a lot of pores in it, and it will also interact with a lot of organic molecules. So a lot of organic molecules are hydrophobic, or they have hydrophobic patches, and they will get caught up in this matrix. So the good news about this using charcoal is it's very good at cleaning water from organics. And what do organics do? Sometimes they add weird tastes, sometimes they add odors, sometimes they add colors. And so the charcoal can actually remove a lot of this from the whole system. I have another picture here I know that shows another design of a filter. You can see this particular one has layers of sand and gravel and the anthracite, and they're calling it coal. Basically, it's all the same stuff. It's some different grades of charcoal. You can get fine grain, you can get kind of chunky grain. There's different qualities that you can get. And we're going to get a chance to use charcoal in Lab 7 when we're trying to clean up some water sample. Okay, so lots of different kinds of filters. And you put all these things together, and often they're calling this mixing, flocculation, clarification, and sometimes filtration. So just want to talk about that word flocculation here for a minute, because it kind of goes hand in hand really with these two things. And it's kind of one of those terms that's used in the water treatment industry, and they're really talking about the coagulation sedimentation stuff. So here's a little schematic showing a water treatment plant of some sort. And what I'm going to do in a minute is draw for you a little schematic as well. But you can see here we have water going in somewhere at the beginning. And you can see we have alum being added, okay? And so flocculation is kind of like, so you add the alum, and notice we're talking about mixing and flocculation. So mixing implies you're really trying to mix things together. So it's usually fast. Flocculation, on the other hand, is kind of a slow, gentle mixing. And the whole idea is, remember, we're trying to clump and coagulate all of the undesirable particles. So if you're mixing things really fast, things are not going to get a chance to settle out. So there's different ways to do this. And you can see this diagram here. The reason why I pulled this one up is it has kind of a maze-like design to this. So the water has to flow through, it has to change directions. And as it changes directions, it mixes a little bit. So that's one way to do it. You see that in a lot of older style plants. Nowadays, we usually have some sort of mixing blade in there that will sort of do it in a slow process. And I'll show you some pictures here in a minute. I like this diagram here because it's showing some of the processes that we talked about. You can see the mixing and the flocculation. And then we have a clarification or settling tank, and then eventually it goes through a sand filter. And then we're going to talk about some of the disinfection and other processes soon. We'll get to that in a minute or two. So here's what a lot of flocculation looks like now. You can see the maze-like system there, and most places are using these, I guess they're called paddle wheels. And like I said, they can be turned on and they kind of move relatively slowly. And I think I have a picture or two from the wastewater treatment plant here. And so you can see there's a paddle here. Right there, you can make out the blades. It's got 4 blades, and that can mix slow or fast. And in fact, in the right image there, you can see it's actually mixing quite quickly, and the water has become very, very cloudy. And I think I have one that's showing the, oh, you can't really make out the details there very well, but at the bottom of that, there are some paddle wheels for the flocculation process there. And unfortunately, you can't see them very well, but they have got a few different systems at our water treatment plant in terms of different sizes of tanks, and they actually have 2 systems, one that's using one type of coagulant and the other is using a different type of coagulant, and one of them is just newer, and I can't really tell you a lot of the details about that. I think I showed you some pictures of some clarifiers, and there's another one of these round circular shaped clarifiers, and I guess we already talked about that a little bit. So here's kind of, I like this diagram here. It shows you your typical system where you've got a chemical feed here. So somewhere over here is the chemical going in, and that's usually the alum. It goes through some rapid mixing, and then it continues to mix into the next system, but just at a slower pace. So we call that flocculation instead, right? And then it'll go into a settling basin or clarification tank of some sort. And then, the water is actually getting quite clean at this point, and in pretty good shape. So there's something there found on the internet, a very large flocculation system. This here actually moves very slowly. These blades, they move around kind of at a very slow pace. I'm not sure where this is, I can't recall, but there it is anyway. Then there's another one. I was just looking for some decent pictures. Unfortunately, they're a little blurry. I apologize for that. I didn't realize there are such bad resolution photos there. Now, these ones here are probably all somewhere in the United States, I'm guessing, because in Canada, we have concerns about things like this freezing up. So we're not usually doing a lot of our water treatment outside. Wastewater treatment is something different. We can do a lot of that outside, and I'll talk about that, of course, when we get to that unit. There's a lot of factors that go into this whole thing, and this is where, if you become a water operator, you learn all about this, because of course turbidity can change during the season. You can also have water being turbid for different reasons. The water could be turbid because of clay, it could be turbid because of organic matter, and those are going to involve different types of treatments. The type of coagulant, like I said, there's different formulations out there, and that may affect the doses and the speed at which it coagulates. And a pH is a big one as well, because pH is going to affect your chemical bindings. You have your aluminum ion and you have your negatively charged ions, and pH can affect that, either make the binding stronger or weaker depending on which way you're tweaking the pH. Okay, so before I do the schematic, I want to talk a little bit about these later processes. I want to talk about disinfection and fluoridation, and then I'm going to draw you guys a little, I'm going to draw you a water treatment plant of some sort. So just before I get to disinfection, right? Remember what I was saying about these processes here. These processes here are mostly just taking junk out. Okay, and so it could be clay, it could be organic matter, but we're looking at larger particles, and we're cleaning up the water, and it could go from being pretty turbid to relatively clean looking. But we also need to make sure the water is safe for drinking, and we need to make sure it doesn't have any bacteria in it. Particularly, we're concerned about fecal matter and disease-causing bacteria. So what we do is we do disinfection. So disinfection, it basically means we're trying to kill or neutralize as many microbes as possible. So notice I'm not saying we're sterilizing, we're not killing everything. We can't always guarantee that we're killing everything when we're doing large quantities of water. So we say disinfect, which means we're killing as many as humanly possible, hopefully to the point where they're barely detectable or not detectable at all. Okay, and there's a whole bunch of different ways to do this. Probably the one that people are most familiar with is chlorine, because most cities use chlorination systems. Some cities use other systems, or they use them in combination. So, there's chlorine here. You can see we'll talk about ozone, and also potassium permanganate. We'll talk about that one as well. So let's talk about chlorination. So chlorine is a toxic gas. Okay, so that's one thing that you should know about chlorine. It's a toxic gas, and this is actually what was used in World War I in some of that trench warfare, where they were gassing the trenches. It's very, very nasty stuff. So usually we're not working directly with chlorine, although sometimes they do in industrial levels. Swimming pools don't usually use pure chlorine anymore, although they used to. Nowadays, they're using a derivative of this. And so let me just show you the chemistry here for a moment, right? So if you look at chlorine here, here's chlorine gas. And if we dissolve it with water, they react. And what do we get? So we get hydrochloric acid and hypochlorous acid, okay? And the hypochlorous acid actually breaks down into this thing here. And this is really what we care about. And so that is a strong oxidizing disinfectant, so it will kill all sorts of microorganisms. And so in swimming pools, like a recreational swimming pool, often what they do is there's different salts of this hypochlorite you can get. You can get sodium hypochlorite, which is basically bleach, by the way. You can get potassium hypochlorite and whatnot. And so if you ever see them sprinkling something into a swimming pool, that's what they're doing. On an industrial level, such as a water treatment plant, sometimes they're using pure chlorine. Sometimes they're using derivatives. Kind of depends on what's going on at that particular plant and who designed it and whatnot. But this is the end game, is we're trying to get this hypochlorite, which is, like I said, you can kind of think of that as the active ingredient in bleach. And bleach will kill all sorts of number of microorganisms. The other good news about this is, notice we have equilibrium arrows here. So if you leave this water long enough, this is what is going to happen, is the chlorine will eventually leave the water. So this is good too, because it means it's not a permanent thing, and it's not going to eventually go and poison the environment as well, which is something we want to do. So it's not a permanent thing. And ingesting this in small quantities does not harm people at all. It's not really a big deal. What was I going to say about this here? Yeah, so bleach, yeah, I guess I was just going to talk about bleach, right? And so if you take a look at this, this is showing, here's what happens when you have hypochloric acid. And if you mix this with other cleaners that might have acids in them, this is something that you never want to do, okay? Only mix bleach with water in your house, unless you know what you're doing. I don't want you mixing bleach with any other cleaners, because if any other cleaners have acid in them, you could be making chlorine gas, and that's something that's toxic, and you don't want to go there, okay? So just kind of a little note of safety for everybody. There we go. So calcium hypochlorite, like I said, and sodium hypochlorite, those are often the compounds that are usually used. Some older places still use chlorine gas, but it's getting less common. So in Fort McMurray, we don't actually use chlorine. Well, actually we do. We use sodium hypochlorite, but what we do is we mix this with ammonia and we make something called chloramines. And so let's talk about chloramines for a minute and why we're using them. So you can see that the chlorine has been mixed with ammonia, and this is basically what you get here. It's called monochloramine. And the reason why we're doing this in Fort McMurray is because a lot of our water is shipped to various places, right? So it's shipped to camps, and it's sitting in trucks for a while. And so chlorine, as I mentioned, it eventually does come out of the water. And it really only takes 1 to 2 days. And so what we want to do is make sure that the water has that disinfectant in it long enough until it gets to wherever it's going, the camps or wherever. Like I said, sitting in trucks and whatnot for a while. And so we use these chloramines, and it's just kind of a little bit more persistent than chlorines. So that's kind of the big difference here. Kind of does the same thing. It's actually not quite as reactive as straight up chlorine, but it does work. You may have heard of these chloramines in the context of swimming pools, by the way. And so these are a different set of chloramines, so dichloramine and trichloramine. And so these are made when people urinate in swimming pools. So the swimming pool has chlorine in it, it reacts with the urine. And you know, if these are found in high concentrations, then it can cause skin dryness and itchiness, and high concentrations, even respiratory problems, by the way. And this is when we know the pool needs to be cleaned out. Usually in most cases, it's not a health hazard other than people getting itchy or anything like that, but it has been known to cause some problems. You can see this is talking about some other trihalomethanes, and these can be formed with the chloramines, and some of them are known to be carcinogens. You can look them up if you're looking for more information on these. I'm not going to get into any of them in any details. I don't actually know a lot about them. Okay, we're still talking about disinfection. I don't know what happened here, why I have the slides repeated. So notice we were talking about chlorine, and now I want to talk about ozone and potassium permanganate. So let's talk about those ones there. So ozone is a gas, and it's made out of oxygen. And you probably know there's an ozone layer in the sky, and it's up there doing stuff, protecting us from the UV rays of the sun. But ozone is actually quite a reactive compound, and we can make this out of oxygen using electricity. And it's actually a really strong oxidizer. And so some places use ozone because it oxidizes and it will get rid of bad tastes and odors. It destroys all sorts of things. And you can see the list of things it can remove: iron, bacteria, viruses, manganese, hydrogen sulfide, which is found, some water systems have a lot of hydrogen sulfide in it, and our tongues are super sensitive to hydrogen sulfide. So if that's a concern, ozone might be the way to go. And so some places have this ozone. We don't use ozone here. Apparently installing these things is quite expensive, and it can be, in some circumstances, quite dangerous. Now, the disadvantage of ozone is it rapidly decays. So it has to be generated at the water site, and usually we have to use chlorine anyway, because the ozone won't last through the pipes going from the plant to people's houses. So, you know, it's one of those things. It's very effective, but we're going to have to probably use chlorine as well. So one other disinfectant that's pretty common is potassium permanganate. And this is something we also use in Fort McMurray as a secondary disinfectant. And this is something that's also a strong oxidizer. So you can see one of the functions that it's doing is it's eliminate many organic compounds, tastes, and odors. So I'm showing you what potassium permanganate looks like in solution. I guess you guys won't be taking organic chemistry next year, but if you took organic chemistry, there is a lab that uses potassium permanganate. So there's been a couple of times over the last few years with the forest fire and the flood. I know I had a letter in my mailbox that said something about this after the forest fire, that they would be flushing the lines with excess potassium permanganate, and your water might turn pinkish in color, but don't worry, this is perfectly fine. And so in fact, I did. When a couple of days after I had that letter, I turned on my faucet in the bathtub, and the water had a little bit of a pinkish color. And so in this case, what they were doing is just flushing the lines with extra disinfectant. This is a relatively persistent compound, just to try to flush the lines out and make sure the water was safe for drinking. Okay, one more thing to talk about regarding disinfection is something that seems to be getting installed everywhere, probably because it's quite cheap. It doesn't take up a lot of space, and it's very effective. And so you're starting to see these pop up, and I don't know if they're in all water treatment plants yet, but everywhere I've heard about it, people have installed these in the past 10 years. And this is using UV radiation. So you probably know that UV radiation has energy to it, and you get it from the sun. And if you get too much, you might get a sunburn, or you might get cancer or something like that. There's different qualities of UV radiation. You probably have heard of, sometimes people talk about UVA, UVB, and UVC. I can never remember which is which, but some of them have more energy than others. And you can see, oh, they're talking about UVC. That must be the high energy one. And what it can do is it can actually break bonds in DNA. And so this is not killing the microbe, but it's basically permanently damaging the microbe's genome. So the microbe can't grow, it can't replicate. It's still, like I said, technically alive. It can metabolize energy, but it's not going to replicate. So if you have a few E. coli in there or something like that, it's not a big deal. They're not growing, they're not replicating. They lack the ability to do any damage to you anyway. So like I said, it's not necessarily killing them, it's more or less disabling them by damaging their DNA. And I did have a picture from the wastewater treatment plant. It was a terrible picture. You're not allowed to go way down in there to show the system, but you can see here's a cartoon I found that kind of shows the system. The water's going in, basically going in a tray, and there's a UV lamp. You can see it's one of these long light bulbs, one of these big long light bulbs here. And it's hitting it with high energy ultraviolet light and basically disinfecting it that way. Okay, so we talked about cleaning our water up, which is these ones here. The aeration, like I said, that's often used for groundwater. We want to kill the microbes. And so at this point, our water is basically, it's good. It's clean. It's hopefully free of odors and weird tastes. The microorganisms are dead. And sometimes there's other adjustments. One of the adjustments that might be done is fluoridation. So let's talk about that just for a minute. I know we were talking about it last day. I just want to talk about at a water treatment plant for a minute or two. So at a water treatment plant, if they're adding fluoride, there's different chemicals that can be used. So you can see we can use sodium fluoride, which is NaF. We can use sodium silicofluoride, which is Na2SiF6, and we can use fluorosilicic acid, I think is how you say that one, which is H2SiF6. I don't really know a lot about these compounds and what their sources are. I think that's one of the criticism of people who are against water fluoridation, is that at least one of these is basically an industrial byproduct. And the concern is that it's not just that, but it may have other toxic things in it, but I'm not really sure. But obviously the whole idea is to get the fluoride in there. And so depending on which chemical you're using, you may have to use a different amount of the chemical, because, you know, like if you look at sodium fluoride, for example, fluoride is 45% of the mass of that, right? The sodium is the other 55%. So you got to make sure you're adding enough of it to get the proper amount of fluoride. And a lot of these compounds too are relatively reactive. So here's, you know, there's safety concerns of those kind of things. You know, these kind of compounds, you don't want to get them on your skin or anything like that as well, in the pure chemical forms, of course. And I think I showed you this slide last day, so I'm not going to dwell on it anymore. So there's kind of our water treatment. There are other things that can be done, but what I'm going to do now is draw for you a kind of a one-pager kind of water treatment plan, I guess we'll call it. And so what I'm going to do is we'll just switch to the whiteboard here in a second. What I'm going to do is kind of draw you a scheme and show you what a typical water treatment system might look like. So let me switch to the whiteboard. So here's my whiteboard, and so what should I title this? We'll call it a typical. Notice I have it in brackets. Water treatment plant. I have typical in bracket in quotes because, of course, there is no typical. Every water system is different in terms of what is going on, in terms of if there's a reservoir, and you know, some cities fluoridate, some of them don't, and all those kind of things, right? Okay, so let's start off with our water source, and this is not identical to everything that's going on in Fort McMurray, because I'm adding a couple of extra features in there. But what I'm doing, like I said, trying to draw something that's typical. So we'll start over here, and this will be our water source. So we'll call this a reservoir, because this is pretty common thing to do. Is somebody, you know, they'll pump water in from a river or a lake, put it in a reservoir, just to let some natural settling going on. Okay, and then usually there's some sort of right at the intake, some sort of grate. So this is my grate here. Okay, so the water is going through that. There we go. And this is a grate, G-R-A-T-E. Okay, and then somewhere right at the beginning, you're going to have your chemical being added. And so usually, as I'd mentioned before, this is usually alum. So I'm just going to add that in there. There we go. And so alum, of course, is a coagulant. Coagulant added. There we go. Okay, and then of course, once you add your coagulant, you want to do some mixing. So I'm going to draw you some amazing art here of a water treatment plant. So I'm going to do a tank like that. So just bear with me. I'm just kind of getting ahead of myself here, making sure everything looks nice. Okay, maybe I'll do some different colors. We'll throw green here. So this is my rapid mixer here. So here we go, my rapid mixer, and we'll give it 4 blades like we had in Fort McMurray. 1, 2, 3, 4, and there we go. It's mixing with my little arrow. Okay, so rapid mix. We'll call that rapid mix. And then notice after that, I have some other tanks, and those other tanks are my flocculation tanks. So what I'm going to do, that's the slow mixing, remember? So I'm just going to kind of make some little paddles like that. There we go. I know they're amazing, aren't they? But keeping things simple, that way I can actually draw it, okay? So this is flocculation. I can never remember if there's 1 or 2 C's. I think there's 2 C's. Okay, and so all of this together, of course, is my coagulation. Okay, so there's the first part. And don't forget, after this, we are going to have, you know, some more settling. So usually there's some sort of clarification going on here. So what I'm going to do is just shrink this a tiny bit so I can fit it in. I'm probably going to wrap around, but you'll see how it works out here in a second. So my water is going to go through there, and I'm going to draw a clarifier. I'll draw one of those circular type clarifiers, and maybe I'll make my water blue. There's my water. So I'm not going to add water to everything here, but there it is there. And maybe at the bottom, I'll draw a little bit of sludge. There's some sludge. And this, of course, is my clarifier. Clarification, of course, just means sedimentation. Okay. So what I'm going to do, like I said, I'm going to wrap things around so I don't have to shrink it too much. So let me just stick that up a little bit. And I'm going to draw my filter right here. So here goes my filter. And I'm going to have my water is going to go like this. There we go. It's all joined up. Okay, so this is my filtration right there. So I'll write a label there, filtration. Okay. And remember, in my filtration tank, well, we'll have water in the filtration tank. So there's the water. And maybe I'll draw a couple of layers of stuff at the bottom. So this will be my sand layer maybe, or my anthracite layer, and maybe somewhere down at the bottom of a gravel layer. So we'll just add a little bit of detail those, make that one a little thicker. Maybe this one's the gravel layer, so it's even thicker yet. Okay, so that's going to go through the filtration. And at this point, I'm going to just have that come out of the bottom at the other end here. And it's going to go all the way to the house eventually. And I'm going to draw the house and a bunch of things in the middle. And then what I'll do is I'll label them here in a second. So let's draw, here's the house. Here's my house. Okay, that's not the most amazing house. The roof's a little crooked, but I think you get the idea. And like I said, I'm going to draw a bunch of things here and then I'll label them here in a moment. So this here, by the way, is going to be a water tower. My beautiful water tower. And I'm going to add a couple of things here at the bottom where we're going to add some more chemicals. So I'm going to add 3 of these. Don't worry, I'll label them and explain them in a second. I just figured it might be easier to make sure if I draw them and can fit them all in, because of course I wanted to make sure I could fit them all in, and I think I got it all. Okay, so let's talk about these and what they all are. So one thing I haven't talked about a little bit, I guess that's coming up on the coming slides, is what we can do about pH and hard water, and we can do that. We can add something called lime, and so we'll get to that in a bit here. And so we also have, there's our chlorine and our fluoride. All right, so what I want to do is label these things. And what I'm going to do, or I'm going to zoom in and then I'll zoom out so you can see the whole thing. But I just want to make sure I can write small enough. So the lime is, this is for adjusting for hard water. So we'll say that hard water adjustment. The chlorine is for disinfection. So disinfection. So sorry about the lack of space there. And this is for, the fluoride is for your teeth. And then this last thing here is the UV, which is of course more disinfection. So disinfect, there we go. And then there's my water tower. And the water tower is basically there for storage. And lastly, we have your home. Okay, so I think that's everything I wanted to add to that. So hopefully all that makes kind of sense. And if you take a look at this whole thing, we're trying to clean up the water before we disinfect it, because of course, every step along the way, we're losing a bit of water. If you think about this sedimentation part here, we're pumping out the sludge, and when we pump out the sludge, we're losing some water with it. So we don't want to disinfect right at the beginning and use extra chemicals and extra cost. We're kind of doing all that at the last stages. So we have the water that we need, and we're not disinfecting any more of it. Like I said, depending on, so this here, by the way, this should be an F negative. I'm just seeing that it's kind of messy there. Let me fix that for you. So we're doing those last stages, adding the chlorine and the fluoride and all those things at the last stages for that reason. And that way they don't have to sit in the system very long as well. Usually there's a storage system somewhere. So Fort McMurray, we don't have a big water tower, but we do have a storage tank up in Abasand, which does the same thing. We have elevation there. We don't need to put it in a tower if it's already elevated by the natural landscape of the hill. I don't exactly know where the water storage is. I've never actually looked into that, but that is helping to give the whole city water at 7 a.m. when everyone jumps in the shower. Okay, so hopefully you like my diagram there. I'm going to kind of talk about a few other processes here that are kind of related to water treatment. And that'll probably wrap up today's lecture, and not quite finish. We probably won't quite finish topic 9, but that's okay. We'll get to there next day. So hopefully everybody got that. I'm going to move on back to the PowerPoint. And so there's all the water treatment processes. There's a couple of schemes there. You can see where I got some of my ideas for drawing these. Depending on what your water source is, it may be extra clean, it may not be clean. Generally, lake water tends to be extra clean. If you think about it, a lake is a giant clarifier. And so lake water tends to be pretty good. River water, on the other hand, it's picking up materials, it's flowing fast, it can pick up all sorts of things. So generally needs extra settling and flocculation and coagulation, all those kind of things. Again, every water source is different. Some lakes are very, very pristine. Some rivers are very, very pristine, and some are on the opposite end of the spectrum. Every place has its own challenges of things it's trying to do. And of course, when it was built, they're going to build things to, what the current technology is at the moment. Which may, influence a lot of nuances. I'm not going to play this video right now. Maybe I will save it for next week. I want to talk about a few other things first. Mostly kind of other processes that may or may not be important. And some of these things I'll touch on in a bit more detail than others. So one thing is that taste and odor control. And so I mentioned that this can be a problem sometimes with groundwater areas, and often the aeration is a good enough treatment. Sometimes they use some sort of charcoal to get it out. In the case of Fort McMurray, we're using the potassium permanganate. I don't think the water here, my understanding is the Athabasca doesn't usually have a lot of strong taste or anything like that, but they do it as just to make sure they're getting down to the standards that they need to get it down to. But every place has its own challenges. Groundwater sometimes has extra challenges in other areas. Sometimes there's certain minerals or things that are in the ground that they need to be concerned about. And it can range from all sorts of things. Sometimes it's just extra hard water, calcium and magnesium. Sometimes they're concerned about pesticides or heavy metals and those kind of things. And all of these things have their own different challenges. And I'm not going to get into any more detail than that. Let's talk a little bit about water softening. There's different ways to soften water. And we apparently used to do this in Fort McMurray, and now we don't. I don't know, apparently they stopped doing this a long time ago. And maybe it has something to do with the standards or preferences or costs. I have no idea. But there's a couple of different ways to soften water. And one is using something called soda ash. So what is soda ash? It's sodium carbonate, right? So this is sodium carbonate, right? Looks like this. So when you throw that into water, you get your carbonate, which is CO3 2 negative. So you're probably thinking, okay, what's the big deal? Well, it turns out that this actually reacts with calcium or magnesium and forms a precipitate. It's if you think about your chemistry 101, calcium carbonate is not a very soluble compound. So if you put enough carbonate in there, it's gonna basically dissolve the calcium, or sorry, precipitate the calcium and magnesium, and and it precipitates out. And so hopefully that will settle out during the sedimentation processes. So pretty straightforward. I don't know whether soda ash is cheap or expensive. I know lime is another common way to do it, and this is lime is actually calcium hydroxide. You can see it would be calcium hydroxide here is calcium OH2. And so that will kind of do the same thing when react with carbon dioxide. It will produce this precipitate right here. So kind of the same idea. So know those two things, soda ash and lime, those are two things that can be done dealing with softening. Some people may have water softeners in their house, and you probably know that if you have a water softener in your house, you got to go buy those big bags of salt. This is using a different process, something called ion exchange. It's a very efficient process, and the way this works is your water softener has a plastic resin in there, and the plastic resin, it's not shown amazingly on this, but what that plastic resin does is you can see on this whole thing here, it's got these little plastic beads, and these plastic beads will bind sodium. And what you do is when your water goes through, the sodium gets exchanged with the calcium. So that's all you're doing is changing one ion for another. So you're taking the calcium out and putting sodium in. And so if your water has to get softened too much, your water actually might taste a little salty from this whole process. And that's kind of how these things work. I'm just looking, let me see here. Just looking at the time here. Maybe I'll finish off on reverse osmosis and mention this here. We'll kind of probably come back to reverse osmosis a little bit later on. Reverse osmosis. Basically, that's exactly what it is. If you take a look on the left, here's your normal osmosis. And so in this case here, you have pure water and you've got salty water over here. And what happens is that water will go from a high concentration of water to a low concentration and go in the direction of the salt. Reverse osmosis, you do the opposite, is you take the salty water and you push it through a membrane and you get pure water on the other side. That's kind of reverse osmosis. This is done in a lot of bottling plants for bottled water. It's expensive. This is why we don't do this with city water, because it would be too expensive to do so in large quantities. Some industries use reverse osmosis in order to get water for their plants because they need extra pure water, but it does cost money. Okay, so 149, I'm going to finish there. I will send out an email today just regarding tomorrow's lab. If you could please send me the data as soon as possible, and I'll get it all together and have it ready for tomorrow's lab. And then we can do tomorrow's lab on Zoom. And once I get your data, I'll send out the completed set and with instructions on what we're going to do tomorrow. Anyway, thanks for coming out. I'll see everyone tomorrow on Zoom. Hopefully you have a wonderful Wednesday.